All right, so we're going to spend one more day talking about Riemann sums. This time we're going to use calculators to speed the process up just a little bit um, for at least a portion of the lesson. So this first one wants us to sketch the graph, determine which Riemann sum will be an overestimate, which will be an underestimate, and then we're going to set up the Riemann sums using 4 subintervals, so 4 rectangles. So our graph is 9 minus x squared. So we know that that graph is shifted up 9. Just in general, this graph is going to go up 9. We know that it's a negative x squared, so it's coming down like this. Plus and minus 3 are going to be where the zeros are. So negative 3, positive 3. So this is our graph. Now, it says, let's see here, sketch the graph. Okay, it says we want to go from 0 to 3, so we're only really looking at this side. And we want 4 subintervals. So remember that delta x equals b minus a over n. So for us, that's going to be 3 minus 0 divided by 4, or 3/4. So they're wanting every rectangle to be 3/4 of a unit wide. So I think I'm going to kind of just exaggerate this right-hand side of this graph so that we can put those things down here. So we know that every rectangle is going to be 3/4 of a unit wide. We're going to have 4 of them. And we're supposed to end at 3. So let's see how this works out. If I add 3/4 and 3/4, I get 6/4, or 3/2. And so 6/4 plus another 3/4 would be 9/4. That doesn't reduce. And then 9/4 plus 3/4 would be 12/4, which is 3. So we do end up in the right spot. So these are where our rectangles for the left and right should fall. Okay, so it wants us to do the left-hand sum first. So for our left-hand sum, using these 4 rectangles, we know every one of them is 3/4 of a unit wide. We're going to have f of, and then for the left, starting on the left, our first one's going to be at 0. The next one would be at 3/4. The next one at 3/2. And the last one at 9/4. Okay, so if we're going to draw a picture of this one's coming up here. These are all under. So this one obviously if you draw it right. Nope, didn't draw it right. Erase those. We weren't using the 3. We were using the 0, then the 3/4, then the 3/2, and then the 9/4. So again, if you draw it right, obviously this one is an overestimate. Of the actual area under the curve. So this is going to be 3/4 times, and then this is where our calculator comes in. Plugging in 0 is easy. I plug 0 in here, I'm just going to get 9. But then plugging in all these fractions may be a little harder, so I would go to y equals and put your equation in. Go to your table setup and put it on ask, and then go to your table and then just start inputting what we need. So for this one, the next thing we need is 3/4. So 3/4 gives us 8.4375. Then we're going to put in 3/2. That 3/2, which gives us 6.75. And then 9/4. So 9/4 gives us 3.9375. And then we're just going to add all that up. All right, so just type all those in there, and then we're going to multiply that times times 3/4. We get 21.094. All right, we're going to do the same thing this time using the right-hand sum, the one I drew first. So this time, still 3/4 wide. We're going to find f of the right would be 3/4 first, plus 3/2 plus our function at 9/4 plus our function at 3. So we're going to plug all those values in. Some of those we already have. The f of 3/4 was our second value here, so 8.4375. The 3/2 was 6.75. The 9/4 was 3.9375. And f of 3, that one's a pretty easy one to put in. We put in 3 right here, squared is 9. 9 minus 9 would be 0. So now we're just going to total all those up times 3/4. So let's see here. So here they are. And then we're going to multiply that by the 3/4 in the front. We get 14.344. And that one is our underestimate. All right, so let's take a look at our table in this next problem. This is the first time they've given us the information in a table, but to be honest, this is way easier when it's already kind of laid out for you. So this one wants us to use the table values to find the estimate of our function from 0 to 6. The area under the curve from 0 to 6, remember, is what this is representing, using three equal subintervals, 3 rectangles. Well, they gave us 6 different intervals, so there's actually 6 rectangles, but we only want 3. So what does that mean? Well, remember our b minus a, our delta x. So 6 minus 0 divided by 3 means 6 over 3, which is 2. Each of our rectangles is going to be 2 units wide, so we're going to go from 0 to 2, and then 2 to 4, and then 4 to 6. So that makes it really easy. We have our 3 rectangles, the left, 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 or the right, right, right. Midpoint, right here in the middle. So it's really, really easy to read these. So part A, right hand using our 3 rectangles. So each of them we know is 2 units wide, and so we're going to be finding f of the right hand, so the 2, the 4, and the 6. If you want to be sure you're using the right, you could start on the far right and just work your way backwards. The 6, 4, and 2 doesn't really matter. But the right hand would be the 6, the 4, and the 2. So just look at each of those values. F of 6 was negative 10.5. F of 4, 2.3, and F of 2, 8.3. So we just type all of that into the calculator. I've already done all that, so this is 0.2. All right, for B, we're doing the left with our 3 sections. So the left-hand side would be the 0, 2, and 4. So F of 0, F of 2, and F of 4. So F of 0, 9.3, F of 2, 8.3, F of 4, 2.3. Again, I already have this one totaled up for us. We get 39.8. Big difference there. and the right and the left. Okay, so the midpoint. The midpoint with these three subdivisions, each rectangle is still 2 units wide, but we're using the points that fall in the middle. So we're using the 1, the 3, and the 5. So f of 1 is 9.0, f of 3, 6.5, and f of 5, negative 7.6. So we total all that up, and that one gives us 15.8. I really enjoy doing the ones that are already in the chart for us because the information is all there. We just have to pull it for the endpoints that they're asking. All right, example 3 is an example pulled from a calculus exam. It's got some questions that have to do with things that we've already learned, and some of the questions have to do with things that we have just learned in our lesson. So this will be a good review problem as well. But in this problem, they've given us a graph and a table. Both of them looks like it represents the rate of fuel consumption. So the rate in gallons per minute, and the time in minutes. We see, the same 0 to 90, and our rate here, 20, which was at 0 up to 70. So these are representing the same thing in two different formats. It says the rate of fuel consumption in gallons per minute recording during an airplane flight is given by a twice differentiable and strictly increasing function. Now, that strictly increasing, that, we talked about if a function is increasing, whether our right or left are going to be over and under estimates, so that's probably going to come into play here. The graph of R and a table of the selected values of R of t for the time interval from 0 to 90 minutes are shown. So first, they want us to use the data from the table to find an approximation for R prime at 45. Well, R prime at 45, or the derivative, the first derivative at 45, would be the slope. And it says an approximation of the slope. All of those are things that you need to be able to interpret for yourself. Derivative means slope. Approximation of the slope means that we don't really need the actual derivative equation. So it says show the computations that lead to your answer. Well, if we're approximating slope, then we can just use the normal average slope, or y minus y over x minus x. So if we look at our table, we don't really have information for 45, but 45 is going to fall right here in between these two values. So to find an average between those would be very easy for us to do. The derivative at 45 is going to be estimated. I guess I should put approximate, the little wavy lines for approximation, is approximately y minus y, or the R at 50 minus R at 40 over x minus x, 50 minus 40. Well, R of 50 was 55, R at 40 was 40, and then on the bottom we've got 10. So we end up with 15 over 10, or 1.5. And this is a rate. It is a derivative. So it's gallons per minute squared, because this was already in gallons per minute, and we took the derivative of it. So it's going to be in gallons per minute squared. All right, so that was kind of an old question. So let's look at B. It says the rate of fuel consumption is increasing fastest at time t equals 45. What would be the value of the second derivative at 45? Well, it says that it's if it's increasing the fastest at t equals 45, then if that's going to be our highest point on the derivative, then that makes it a max. And if it's a max, then the second derivative at that point would just be 0. Because at a maximum, we have a horizontal tangent. So that's what we need to say. They want us to explain it. They say explain your reasoning. So you have to be able to think through that. If it's the fastest at 45 and r prime of 45, is our high point, then that's going to be our maximum. And the second derivative of that maximum is 0. So let's just see how we could write all that down. They have a place for us to do this on the back. So first of all, I would state what I think. I believe that the second derivative at 45 is going to be 0, and then I'm going to explain why. So I know that the first derivative at 45 is the rate of fuel consumption. And since r prime of t is the greatest, or the highest, or whatever they said, at t equals 45, then this is a relative or local max for r prime of t. And since r prime of t, or r prime of 45, is a max, then the second derivative at 45 has to equal 0, must equal 0. Now, there's probably other wording that you could use, but you need to use what they've given you to explain why you came to that conclusion. All right, so we're going to flip back over and look at part C. Here we go. All right, so again, A and B, they were really not anything new. That was old information, but it looks like this next one is going to be part of our Reimann sums. So let's see what it says. Approximate the value of the integral from 0 to 90 of r of t using a left-hand Reimann sum with 5 subdivisions as indicated by the table. Is this approximation less than the actual value or not? I mean, they just want to know if it's less, so it's going to be yes, it's less, or no, it's not. And then they want us to explain. Now, this is the first time. Usually we do 5 equal subdivisions, but it doesn't say equal. And that's good, because if we look up here, we've got 1, 2, 3, 4, 5 subdivisions given. 1, 2, 3, 4, 5 subdivisions. And so they're not all equal, though. Well, yeah, no, they're not. This one's at 30, this one's 10, this one is 10, this one's 20, 20 again. So the thing is, we've been putting delta x, or the width of our rectangles, the same on all of these, but for this one, when we total it up, the difference between them is not all the same. The difference here is 20, 10, 10, 20, 20. I don't know why I said 20, that's 30. 30, 10, 10, 20, 20. I think I got that right. So, then they told us to use the left. Let's see. Did they say left? Yeah, left. So the left would be the 20, 30, 40, 55, and 65. If they had said right, I would have started at 30, used 30, 40, 55, 65, and 70 for my heights. But for the left, these are going to be my heights. So my first rectangle is going to be 30 times 20. The second rectangle, 10 times 30. Third, 10 times 40. Fourth, 20 times 55. And fifth, 20 times 65. So that's what we need to write out. Okay? So is everybody good with that? 30 times 20. 30 times 10. Okay. So I'm going to have to flip this over to write it all out. So here we go. Left-hand sum, 5 intervals. And then I think the first one was 20 times 30. And then we had 30 and 10. And then we had 40 and 10. And then we had 55 and 20. And then we had 65 and 20. So if I total all of that up, I get 3,700. All right, so let's look back at the question. It asks us to approximate this, which we've done, and then it asks, is the approximation less than the actual value? Okay, so this function, it told us here that it was increasing. That, if maybe you forgot, you could go back up here and look, well, if I use these left ones, are my rectangles going to be too high or too low? Well, of course sorry, you can see what I was drawing. It looks like they're all under. And if they're all under, then this is an underestimate. Or if you remember, for an increasing function, the left-hand values are the underestimate, and the right-hand would be the over. So this one is less. The Riemann sum is going to be actually less. And we probably need to state that that's because R of t is increasing. All right, so let's take a look at our next question here. So it says, for the interval from 0 to 90 minutes, explain the meaning of the integral from 0 to b, which is somewhere in between the 0 and 90, in terms of fuel consumption for the plane. And then it says, explain the meaning of 1 over b times the integral from 0 to b. Now this, right now, it's something that we're really going to have to think about, but this is actually a precursor to what we're going to do in the next lesson or so. But if we can understand it now, then it's going to be way easier when we get to it to understand. So it says, so what does this mean in terms of fuel consumption of the plane? And indicate units of measure in both of your answers. So let's just talk about what this integral means again. Remember that the integral is the area under the curve. And when we first talked about this area under the curve, we had like a velocity function. And what the area under the curve gave us was the distance in, I think it was miles. So it was in miles per hour, and the area under the curve gave us position, or in miles, or distance in miles. So with that in mind, if I am integrating something that has to do with this fuel consumption that is in gallons per minute, then whenever I find that area under the curve, I should be finding gallons of fuel. So if the rate, or the velocity pretty much, was gallons per minute, then my answer under the curve is just in gallons. So as far as describing what this means, the integral from 0 to b of r of t with respect to t would be the total number of gallons. of fuel that was used from 0 to B minutes. Okay, now, if that's the case, if this is giving us the total number of gallons that have been used, then what do you think if I were to take this integral from 0 to B of R of t and divide it by B? That's the same as 1 over B times the integral from 0 to B of R of t. Now the reason I wrote it like this, if I had said, okay, we went 40 miles, this integral gave us 40 miles in 4 hours. Then 40 miles divided by 4 would give me 10, which would be the average number of miles that I travel per hour. So this is just giving me an average. If I divide by this difference right here, then I'm really just finding the average. So this thing gives me the average number of gallons used in this case per minute, because that was what was in our chart, from t equals 0 to t equals b, from 0 to b. Now, they gave us our units of time. They gave us our rate in gallons per minute. That's how I know that it's gallons in minutes. You know, in our original graph, let's see if I can find that real quick so you'll see. Maybe you can know what I'm referring to. This was in hours. Our velocity was in miles per hour, and it gave us miles, right? The area under the curve gave us miles. So the same idea here. Gallons per minute, units of time minutes. Whenever I find the area under this curve, I'm finding the number of gallons. So, and then if I divide by that number, so in this case, if I had divided this by 3, I would get an average of 40 miles every hour. So here it's an average of whatever this is in gallons, average of gallons. All right, so pretty interesting application problem here at the end. But prior to that, remember what we did here was just a left-hand and right-hand sum. We talked about how you can just type this in the calculator so you don't have to always worry about these fractions and the decimals that those are going to give you. Also, we talked about these tables. The tables are usually pretty easy to read. And this one was in equal subdivisions, but you know, this one that we just did, this application problem, these were not all equal. And if they're not equal, then whenever we write them out, we have to put that width with every one of our heights. So 30, 10, 10, 20, 30, I should have written these, 10, 10, 20, 20. These changed every time. So we had to write them all out. Whereas here, since they were the same, we just pulled it out to the front. So don't forget that sometimes those subintervals are not equal.